Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 15. We're still talking about straight line regression. This is part 3, and there's going to be several more parts after this. So in this chapter, we have these 10 or 9 areas we're going to discuss. Today we're going to discuss performing inference about the slope and the intercept. The slope is beta 1, the intercept is beta naught. Before we go, let's review what we did last time. Last time we talked about the best fitting straight line, and we discussed the least squares method and the fact that the least squares method means that the sum of squares of error are the minimum that they can be. So the choices of beta naught hat and beta 1 hat are the choices that minimize that sum of square error. And then to assess the quality of fit in a general sense, not in a testing sense, but in a general sense, we looked at the sum of square error and divided it by its degrees of freedom, n-2, which made it the mean square error, and that is the estimate of sigma squared, the variance that's supposed to be the same for every value of x. So for every fixed value of x, the variance at that value is supposed to be sigma squared, and that is estimated by that mean square error. Okay, so in this video we're going to talk about these inferences about beta naught and beta 1. So the slope is beta 1 and the intercept is beta naught. So we need to take into account the uncertainties in the sample data. And so to do that, we calculate confidence intervals at times, and sometimes we perform hypothesis tests. In fact, we usually do both, and we're doing this on these unknown parameters, beta naught and beta 1. Beta naught being the slope, the intercept, and beta 1 being the slope. We have y equals beta naught plus beta 1 x plus e. And we said that our estimate for beta naught, we would come up with y hat equals y bar plus beta 1 hat x minus x bar. That is substituting in for beta naught hat. Okay. And these confidence intervals and hypothesis tests, for us to perform those and to calculate those, the data has to be, y has to be normally distributed for each value of x. So again, if you recall back to the pictures that we had before, we would have a x across here, and for each value of x, we would have a distribution, and we require that those distributions be normally distributed and that the variance for each of these be the same. Okay. So y1, y2, all the way up to yn has to be mutually independent for each value of x. Okay. So given each value of x. This means that beta 1 and beta naught are normally distributed with means of beta naught and beta 1 respectively. So let's look at the sampling distribution of the slope. And so we take the expected value of the estimate of the slope, beta 1 hat, and we plug in, so this is the expected value, and we plug in our estimate here. And there's a lot of algebra that goes on. I won't bore you with it, and this is an applied class, not a theoretical class, so we won't get into deriving this. But when we get finished, we end up with beta 1. So E of beta 1 hat is equal to beta 1. That's nice. The expected value of something is itself, the expected value of the estimate is the population parameter. That's exactly what we want. So if we take the variance of beta 1 hat. Again, there's a lot of algebra and derivations, and then we get to this nice, fairly nice expression here. And so this is basically n minus 1 sigma squared over s sub x squared. Another way to write it. Multiply top and bottom, or yeah, divide, let's see, I'm sorry, I have it wrong, don't I? This is, if I multiply the top and bottom on the bottom, if I multiply on the bottom by n minus 1 over n minus 1, sum of x minus x bar squared, we get this quantity here is s sub x squared, and then we'll have n minus 1 on the bottom. I thought that looked wrong, and it was. So there's another way to write it. Okay. And then we take the estimate of this variance. That's what the hat over the var means. And to do that, we substitute in for sigma squared, which we don't know. We substitute in with its estimate, SSE, and another way of writing that is s squared sub s sub y given x squared here. Okay? Oh, and here I have that other form here. Okay. So that's our estimate there. Now, from statistical theory, you'll learn this in in Math 311, that this quantity here, if we take beta 1, some estimate, beta 1 hat, minus its expected value, that's what beta 1 is, divided by the standard deviation of this estimate, then that has a t-distribution. In this case, it has n minus 2 degrees of freedom. And s sub b hat 1 is what we just derived, or, well, just showed up here. So it's that s sub y given x over s sub x square root n minus 1, and this is SSE, sum of squares error. Now, the confidence interval for beta 1 is given by beta 1 hat plus or minus t n minus 2 degrees of freedom. You'll see that a lot in the straight line, and 1 minus alpha over 2 for our area on this side of t. Okay, and then times our estimate here that we came up with, the estimated standard deviation for this beta 1 hat. The hypothesis test that we would perform on this would be that beta 1 is equal to some beta 1 naught, usually 0. So some value that we want to test whether it's equal to that, or actually we say that we assume that it is equal to that, and then we try to prove that it's not. And okay, and again, the test statistic is given here. And then our alternative hypothesis could be one of these three. Either beta 1 is greater than beta 1 not 0, or it's less than, or it's not equal to, and that changes our rejection region, or I like to call this the rejection criteria. If this statement here is true, if this is true, we reject H naught. Otherwise, we don't. And so if our test statistic is greater than this value, we'll reject. If it's less than this, the negative of that value, notice this is 1 minus alpha, not 1 minus alpha over 2. So if it's greater than this value here, then we'll reject. Or if we're doing the less than, if it's less than this, the negative of this value, then we'll reject. But if we're doing not equal to, then it either has to be smaller than the negative, using the 1 minus alpha over 2, or greater than the positive, using, again, 1 minus alpha over 2. Another way to write this, or do this easily, is to say take the absolute value of our test statistic. If it's greater than this value, reject under this alternative. Okay. Now let's look at the same thing, the sampling distribution of beta naught. And you'll see that it's very similar, except actually the derivation's a lot easier here. So I put it here, but I won't go through it. So beta naught hat is equal to y bar minus beta 1 hat x bar. And the expected value, as we would hope, of beta naught hat is the population parameter beta naught. The variance of beta naught hat turns out to be this lovely expression here. Notice the 1 over n added to, and we've got the x squared here, okay? And we've got sigma squared out here. So we've got some extra terms in this. And then the estimated variance of beta naught, and this is where we have the hat here over the variance and the hat over the beta, that's equal to SSE right here times the 1 over n plus x bar over this. Okay, so I misspoke up here. Yes, okay, never mind. That's good. All right, so now we have our estimated variance, and we can perform our confidence interval for beta naught, the slope, or not the slope, the intercept. And so we can perform or calculate a confidence interval. Again, it's the same format, but now we have S sub beta naught hat instead of S sub beta 1 hat. And of course, that is given by this expression here, where we take the square root of the variance. And the t statistic is the same, though. Okay. Now, the hypothesis test, again, we're looking to see if the intercept is equal to some value, and a lot of times we're interested in whether this is 0, this hypothesized value. That's what this complicated looking notation stands for, is a hypothesized value. Okay. The test statistic will look the same or similar. This is beta naught hat minus the hypothesized value divided by, we could write this S sub B naught hat. I've just plugged in the actual value for it. Again, the rejection region, so based on which alternative hypothesis we're testing here, greater than, you see greater than. Less than, you see less than. Not equal to, you'll see an absolute value. Excuse me. So again, notice that there's 1 minus alpha here, but on the two-tailed test here, the not equals to, we have a 1 minus alpha over 2. Okay. Table 5.2 in your book is very, very nice. It may look a little intimidating, but if you take your time and look through it, it's very good. You may want to copy this into your notes or for your formula sheet. Okay, so that's it for this lecture. Don't forget to scan your lecture notes in by midnight on the date listed on the course calendar. Be neat, because these are for you. Update your formula sheet with a lot of the formulas we went over today. If you have questions, please come to virtual office hours. If none of those work for you, then by all means, email me. I'm happy to help you. We'll see you next time.